Okay, everybody, welcome for today's third webinar session of this webinar series. A brief due introduction to Mr. Abhishek Goswami. I will start. Mr. Abhishek is our ISM alumni of MSc Tech Applied Geophysics 2000 batch. He has recently moved into a new role as a senior technical data management consultant at Shell UK. He has expertise in global business guiding global business strategies to optimize oil and gas exploration and production. So, Abhishek, sir, I'm looking forward to your speech today here. Over to you.
Thank you, Ishika, for your kind words, and good evening to everyone who's managed to find time and dial in today. First and foremost, I hope you can hear me clearly. I did manage to unmute myself. And if you haven't, one of you, it's probably a good time to start recording as well, so that we could tell the audience that if they need to go somewhere or miss out for some reason, they can always listen to the recording later on. Welcome to the third talk of the session and my second. And here I will delve into seismic interpretation. Now, interpretation itself, it is a combination of pattern recognition, something we call mental filtering of seismic data, and the experience in seeing through the seismic using a very important thing called geological insight. It is the ability to discern and describe depositional settings, structure, and stratigraphy, notwithstanding the challenges of poor quality data and the inherited limitations. So, what are we going to do today? And this session, we will try to standardize a workflow for seismic interpretation. It is tricky simply because such standard templates do not work, because every data set, every part of the world is inherently different. So this is very generalistic and is very flexible depending upon what you encounter. I have a lot of ground to cover to keep enough time for a good comprehensive Q&A, which I'm expecting today. So moving forward, let me see. Why isn't the slide sort of working? Okay. Everyone able to see the second slide? It took a little time to move.
Yes, sir, it's fine.
Oh, good. Okay. The agenda. The first step is, again, I will look at it with a bird's eye view. What does building a hydrocarbon resource model mean? What does it look like? I will very shortly touch on something called a stakeholder map. A geophysical seismic interpreter doesn't sit alone and pick seismic. Some people may tend to think that way. I will dispel that notion. We will then get into the business end of this presentation, which is structural interpretation, how we massage our data, how we then go about and interpret a seismic volume or a set of seismic volumes, how and why do we do attribute analysis, and how does that lead to fault interpretation. Then I have a serious challenge of trying to cover a subject which would take usually days to cover in one slide, which is depth conversion. And then I will summarize my talk. So let me see. Right. Okay. Do not get too flustered or overwhelmed by what you see on your screen. It is a bunch of flowcharts with lots of arrows moving here and there. Don't even look at it. Let us break it down into chunks of various phases. If you look at the top left corner, if I try and make the sticky counter work, can everyone see the red pointer?
Yes, sir.
Okay, good. So seismic acquisition as the top left corner and planning a well at the bottom right corner. If you sort of keep that in mind, and now let us go through various phases. The first phase is what we have already covered in the first 2 days. We now have processed data at our workstation. Data we are going to review to take the next step forward. Okay, what is this next step? At this second phase, we take the data and start our initial structural interpretation. Now, this is done in the 2A time domain. That is the same domain in which the data was acquired. Structural interpretation begins with a regional understanding of structure and stratigraphy. This is also the time to understand the quality of the seismic data, the limitations associated with the acquisition and processing of it. As an ex processor, I always check the processing sequence on the EBCDIC header, if not the full processing report, before I start interpreting any data. Once structural interpretation for faults and horizon are over along one workflow, which you can make out again, let me get my red pointer over here. What we tend to do is we do a time and basically take them to what is called the structural framework modeling. Now, this would require a velocity model, which I will come to when I talk about time to depth conversion. The other branch of the workflow then would be to take the data set through a series of steps involving forward modeling, fluid and lithology substitution, wedge modeling, AVO analysis, and finally, in some cases, inversion. Collectively, these are classed together as quantitative interpretation. Once you prepare a rock model out of this, you then time depth convert it again back to what is called a reservoir architecture modeling stage. Um, then what do we do at the third phase? At the third phase, this is the static modeling phase. Here, what we do, this is all in depth because we've already done our time to depth conversion. A framework of horizon and faults are created before setting up a structural model in a modeling tool like Petrel, which I'm sure you've heard of. While the structural model is the first step in creating a property model, the structural framework leads to a very important study called fault seal analysis, which also feeds in. So you've got structural framework with QI information going via reservoir architecture into property modeling. You also have something called fault seal analysis feeding into it. Just close your eyes and think about your house, a clean house which has just been constructed. So if you think your floor and your ceiling are your horizons and your walls are your faults, then once you move into the house and bring in all the furnitures and lay them out, think of them as the properties. So once a structural framework is in place, you flood the zones with various properties like porosity, permeability, and so on. Okay, what happens at the next stage? Now, this is also a very important stage. It is the point at which the structural property, the static property model, we call it static because it doesn't move. It is upscaled into a simulator and converted into a dynamic model. And this is mainly done by reservoir engineers. So that is when you put hydrocarbon and water and brine through the system. Now, geomechanics, which Partha will cover on day 6, is also an area which is an integral part at this stage, and it feeds into the reservoir simulation. Right. Finally, at the last stage, what we have is static and dynamic model information are both used to monitor reservoir performance, how we are doing, and also to identify new targets to drill. For the sake of today's talk, I will be focusing entirely on phase 2. Moving on. As I said, I will just spend a very few seconds on this stakeholder map. This is just to establish that seismic interpretation is not a standalone job. While a lot of work, be it depth conversion, QI, could, depending upon the size of the company, be done by the same person who is doing the seismic interpretation. At times, you have dedicated, certainly for QI, at times you've got dedicated teams and you have to work very closely with them. Likewise, the sequence stratigraphic interpretation is also sometimes done by specialists, geologists, people with huge experience, and you need to work very closely with them when you go past the structural interpretation and get into stratigraphic interpretation. This is the realms at which biostratigraphers, geologists, and also structural geologists have a lot of role to play. The bit that we are going to talk about today, structural interpretation, you really need specialist geologists to bring your fault and fracture prediction story accurate. As a seismic interpreter, you will follow the seismic signal, but structurally, does it make sense? Do the faults actually terminate the way you have terminated them? You need to corroborate with a specialist. Again, this just goes on to show how integrated a process this is. Okay, now we have got, as I said, into the business end of things, which is how do we go about and do structural interpretation? Really, to be honest, you start with getting your data sorted. So, importance of noise suppression for interpreters, I cannot basically say with more conviction. Noise suppression is a critical element. Noise alone can make or break your interpretation. A noisy data set makes detection of steep structures and small faults very difficult. So you have to increase the signal to noise ratio in your seismic. Okay, I intentionally kept the noisier section away. So now when you compare what you had on the right to what you have on the left, you could see that how much of work has gone into making what look like this section here and the internal reflections in this section here to what you start seeing on the sections to the right. So in this case, what we have done is we have used structurally oriented filters which are edge preserving. In other words, you really do not want to go too hard, because then while you are taking away the signal, you may also end up you're taking out the noise, you may end up taking up the signal as well. So you want, especially for fault interpretation, you want these edge preservation methods to work. Okay, so now we have data set which is good signal to noise ratio, and you are at a point where you can start your horizon interpretation. The question is, which interfaces need to be defined? Where are my major discontinuity surfaces and sequence boundaries? Am I picking unconformities? There are questions right up front. If I have a predefined reservoir, we need to map the top and base unit. Surfaces with a significant velocity and or density contrast, in other words, you multiply them and you get impedance, that is what needs to be mapped. Geologically, they can be maximum flooding surfaces, or you could have something like an abrupt change in lithology. If you remember this C stack I showed on day one, I just did a PowerPoint interpretation on one such strata. Just think of it as if this is your reservoir, and I've just gone and picked a top and base unit of the reservoir. I mean, you get abrupt changes in lithology in so many situations. You go from sandstone to chalk, from shale to dolomite, you get these changes. There are also other things what I call outstanding events. Now, outstanding events in the North Sea, we have regional markers which are pervasive over hundreds of square kilometers. One such one, I have got a slide there coming. Now, I think it's the next one, where we will show how the base Cretaceous unit, or what we call in short BCU, is mapped regionally. But there's one more thing which I'm not doing a great deal of service by talking about it through one single bullet point. It is the seismic to well type. Once these markers are established, this very important step of tying your seismic to your well data needs to be done to establish the nature of the peaks. In other words, what am I picking? Am I picking a peak? Am I picking a trough? Or am I picking a zero crossing? Once the well tops and events on seismic are properly calibrated, only then are we ready to pick events on seismic data. As I said, this is just a seismic section, a cross section. It is taken out of, this is 3D data. And I will just at my next animation show you an event that we pick regionally. There you go. So this is the classic BCU, which on a map looks like this. And I mean, I have just picked it or shown it on a line. You can pick it over hundreds and thousands of square kilometers in the North Sea. It is also a very important pick because underneath it lies the Kimmeridge clay, which is the biggest source rock for hydrocarbons in the North Sea. Okay, so how do we do it? We have talked about what do we do. Let's get into the how aspect of it. In the good old days, detailed interpretation was quite laborious. It was done in what we call the seed grid approach. Basically, you have an area to interpret, you go line by line, you go to track them, and you try and create a map. This has gone on, and in some areas, if you only have 2D data, this is still practice. But at the same time, things are changing. And now we are insisting on moving away from it. Into what? Away from seed grid, use of modern volume auto trackers and editors. Why? We do this to maximize the information extraction from even larger and, more importantly, multi-volume surveys. By multi-volume, what do I mean? I mean you have legacy old data, you have new data, you have various angle stacks and substacks, near, mid, fars, that you pick up, and it's physically impossible to do multiple interpretation of the same horizon using different data set. In other words, you need something in 3D space. So on large 3D surveys, the conventional grid-based approach is too time consuming. Also, for quick turnaround interpretation on normal size surveys, we tend to use 3D volume interpretation. The caveat, we can only do it if the data quality is reasonably good and we have enabled IT infrastructure at our disposal to make this happen. Okay, so if I have now gone and picked my horizon, the next few slides I will show you a quick cartoon. Just a series of horizons starting from the seabed down to the base of the target area of interest. We now have multiple horizons ready to be taken to the next stage. So yeah, as I said, let me just walk you down these. So we are now probably going through some overburden horizons, down, and this is possibly the top of the reservoir and maybe the base of the reservoir. The blue things that you see are the wells that have been drilled there, and then finally this is the last event which was possibly drilled, which was locally picked. It clearly hasn't been picked aerially. So yeah, go back again and start. And then bear in mind, this is the geological cross section, which is also changing as I am stripping one layer at a time. Okay, so this hopefully gives you an idea of what horizon interpretation looks like. What is the scheme that we employ to do this work? Now let us move to something quite interesting. It's called seismic attributes. Now, people in the call who have heard about seismic attributes, one question that's often asked of geophysicists are they just pretty pictures? Are they not what the seismic data, the reflectivity data already tells you? Basic attributes are based on three characteristics of the trace. It's the amplitude, frequency, and phase. For this part of the study, we will focus mainly on the amplitude attribute. So, if I keep things very simple, attributes equal to filters that throw away data to highlight or quantify some geological feature of interest. So, the question is, what are we trying to highlight and capture? Again, I will say, in conventional workflows, we would pick a horizon. Then we would calculate what is called a dip attribute and an azimuth attribute, as you see on the map here. These, when you see an anomaly on the dip attribute, all it is showing you is in the horizon interpretation, there is a degree of abruptness which could be due to a fault. So it's a pretty simple attribute to calculate, and it certainly gives you idea of where the big changes in amplitude, which could correspond to a fault or not, are. But we need to go beyond that. So what we do now is we use a method which works really well for flagging discontinuities or abrupt changes based on lateral change of the seismic waveform. So in other words, in a trace by trace computation of this attribute, which I'll name in a moment, if you have got one trace going to the other, you don't get a high anomaly number because they are the same. Whereas as soon as you see a change in the waveform, it immediately flags it with a high number. And this could, in most circumstances, correspond to a fault throw that is being depicted. So the attribute that I'm talking about is, in this case, it is the semblance attribute, also called the coherence in some algorithms. And there are different kinds of semblances, regular semblance, sharp semblance, or structurally oriented, which are edge preserving, as I said earlier. So what we tend to do is we make these, this is the reflectivity seismic. You could make out the faults, but you really start seeing them nice and well on the semblance here. And this is looking at the same semblance from a cross-sectional view here to a slice view on top. So you look at semblance and you combine them with dip and azimuth before you get a clear idea of what is the fault story in your area before you actually go and pick faults. So this is almost like a data preparation before your actual fault interpretation. So why don't we move to that? Once the attribute analysis is done, let us now move into the territory of fault interpretation. What is the goal here? The goal here is to understand ways to tell if fault interpretations are geologically valid. You need to strategize for that. So what strategies am I talking about? Get an overview of fault complexities and structural style. This is exactly what I was doing in the previous slide. The good thing about attributes is it just works on the data. You do not need, in some cases, you may need a few horizons picked, but otherwise, you really do not need any faults picked. You just need the seismic data. So this will very quickly give you an idea of how complex this architecture is. In other words, how much time is it going to take you to do the fault interpretation? As quickly as possible, get an overview of structural shape prior to focusing on a prime objective. This is important. What are we looking at? Are we looking at a perfect anticline, four-way dip closure? Or are we looking at a fault-bound anticline, which has three-way closures and a big fault on the other side? Do we have salt diaparism here? Do we have gas chimneys here? These are the kind of things that you need to see right up front, and that will heavily impact what your fault picking strategy is. Where significant faulting occurs, interpret faults before horizons. Now, this is also a technique which a lot of people use. They do not start with horizon interpretation. Rather, because fault is there in the seismic data itself and the attributes bring it out nicely, they just focus on the fault interpretation. And once the fault interpretation is done and you have these nice boundary constraints, you use that to try and understand what is the throw in the faults by picking horizons on either side of it. Just another approach depending upon your data. Yeah, and I always agree with this particular bullet point. You should always focus on your major faults first, your basin bounding faults, your big faults in the system. Because once you get into the minor faulting of what is happening within the reservoir, how your reservoir units are compartmentalized, it takes a lot of time. Sorry. And last but not the least, this is where a structural geologist's help becomes very important, that you get an impression of fault hierarchies, conjugates, and cross-cuttings. This is when, let me show you the diagram, when you have very complicated fault systems picked, you need to understand, say, for example, if you look at this red fault, this is possibly a primary fault, and you have an antithetic system to it, which is this one. Sorry. So in terms of juxtaposition, in terms of which one terminates against what, you need to get the structural story right for them. So QAQCing, once you have picked these faults, QAQCing them is also very important. You need to make sure that when you look at a fault plane, say for this particular fault, you need to make sure that the throw of the fault is consistent all along. Sorry. You need to make sure that a normal fault doesn't become a reverse fault just because you haven't been consistent in your picking. Okay, so post fault picking, we now have to move into something which I said is quite tough to do in one slide. I will try it. Let me see how I'm doing for time. Yeah, I still have about 10 minutes, so I think I can carry it off. Now, why do we need depth conversion? If this was a classroom, I would have a really interactive session at this point. However, due to scarcity of time, let me get to the point. While you record seismic with 2 at a time as the z-axis and interpret while in the time domain, you still plan to conceptualize your wells and then drill them in depth. So at some point, you have to bring everything in the depth domain. In other words, to obtain structural data positioned in depth from data recorded in time domain, you need depth conversion. This conversion, by the way, makes extensive use of a particular rock property, which I'm sure you all know. It is called velocity. And we have so many of them. Velocity modeling itself would require a lot of time to cover, but certainly the basic one, you would have sonic logs, you would have check shots, just to name some of the velocities that are there. So we need to make maps as well, maps of reservoir in depth and then calculate volume. So the first step is to define the objectives and find out what data is available. Then developed a strategy for time to depth conversion and what is achievable. There is also something called uncertainty, which I will again touch upon. Uncertainty to do with so many things, but right now let us just focus about the velocity field. There is also uncertainty around the time horizon that you have picked. So they need to be also included in the depth conversion strategy. because ultimately they are going to make an impact on the ranges of your volumes that you calculate. You just don't go to management and say, oh, we have 10 million barrels of oil equivalent in this area that I have mapped. It doesn't work that way. That may be your base case. You always need a low and a high. And that low and a high volume is more often than not derived by a low and a high map. So the low and a high map comes from your uncertainty analysis. Okay, so let's move along these chevrons one at a time. So first step, as I said, is QC your seismic data. Wrong seismic pick at the well intersection results in a wrong velocity model. So you will be underpinned by completely wrong assumptions right at the start. Then you come to the velocity model step. Build a velocity model. Always start. I mean, I've put various types of velocity model here just so that you know that we don't, the model building itself is not just a simple process. But what you should always do is start with a very simple model. And just like Partho was talking about imaging and depth imaging yesterday, it is a very iterative process. You work on velocities from starting with a simple model, you depth convert, you then tie your wells and look at the well tie error. And if they are high, you know that you need to make your velocity model a little more intricate because a simple model is too crude. And then you basically go from one scheme to the other, making them more and more complex. So that's how the velocity modeling part works. What you then need to do is you need to analyze your results. So after the velocity model is built, you need to tie the computed depth horizons to the well markers and update the velocity model to incorporate this tie step. And once the analysis is over, you then, once you have established that, yes, I have found what velocity model I'm going to use, you do that for one final time. You then assess for uncertainty. Now, uncertainty is could be a result of so many things. You can get depth differences out of the various velocity model. Each velocity model will give you an error which is very different from the other one. So you can add all these errors to understand how much of plus minus uncertainty, say in meters. Is it at plus minus 20 meter? Is it plus minus 40 meter? So if my reservoir depth is going to be at 5,600 meters, should I assign a plus minus 100-meter uncertainty about it? So doing your depth conversion using various steps and analyzing the results will give you an understanding about uncertainty. Last but not the least, when it comes to reporting, you need to make sure you deliver, as I said, a base case map as well as a high case map. A high case means you are saying that the volumes are going to be higher than the base case, and a low case map where you are being very conservative and saying, no, the volumes are actually much less. So this, in a nutshell, is the workflow of depth conversion, where you really need to assess whether my well markers are good, whether my time to depth strategies are all in place. Try out various, the term that I will use is layer cake models for velocity model building. Convert all your two-way time horizons and faults that you have made in the previous steps at this second step and the fourth step, convert them to depth, tie them to your wells, look at your results, your error between your well marker and your seismic marker, go revisit in an iterative way, continue to fine tune the model till you're happy with it, and then based on it, do your uncertainty. And once you're happy with the uncertainty, add and subtract it to your base case so that you have got a range to report. Okay, now time to summarize. What did we go through? First and foremost, noise cancellation. Getting your data ready for interpretation is almost as important as interpretation itself. Random noise attenuation can greatly enhance interpretability of seismic data. No 2D or 3D project are done without doing this particular step. While opting for filters, one thing to bear in mind is please prefer structure oriented edge preserving data. Otherwise, they will start harming your primary signal, which you want to preserve. Next, I touched upon why we should do 3D volume interpretation over seed grid 2D picking. It is important to understand the paradigm shift from the 2D pseudo grid interpretation to proper volume interpretation in 3D. Earth, the structures, they are all in 3 dimension. Sometimes with 2D interpretation, the interpreters establish regional markers across large impedance contrast. Do your well tie exercise carefully and then select major interfaces to pick. Then only you are ready for horizon interpretation. When it comes to attributes, certain attributes such as dip and azimuth along picked horizons and coherence semblance on volumes are very effective in highlighting structural discontinuities. Remember to always complement semblance with volume and dip azimuth to highlight subtle faults. At this point, you start your fault interpretation. You really need to know the strategy to identify and pick significant faults first, expand into detailed faults, and then into relationships and QC these fault interpretation at every stage of maturation. Depth conversion is needed to obtain structural data positioned in depth from data recorded in time, as I said. But you do that with the help of layer cake velocity models, which basically represents the variability that you see in rocks, both laterally and vertically, and allows a combination of several sources for velocity information, including your migration velocities, your sonic velocities, your check shots. So, finally, once everything is done, you now have a set of horizons, you now have a set of faults. They are all in depth domain, sitting very closely to your wells. You are now ready for modeling your data in a software like Petrel. Okay. So over to you, Ishika.